Hi YouTube, Connor here, and today I will be talking to you about polarization, transmission, and reflection. Now we'll start with polarization, which can be defined as the orientation of oscillation in a wave. Now what we see here is the formula for the electric field in a planar wave, which is a time harmonic wave propagating in the z direction and having an oscillation in the x hat and y hat directions. We can see this graphically either over z hat or time, where we have an amplitude ex and ey in either the x hat or y hat directions. If you look at the xy plane, you can trace the tip of the electric field, which gives us a line with an angle defined as arctan of ey over ex. This line is a special case of the general form, which in phasor notation is ex x hat plus ey e to the negative j phi y hat e to the negative j bz. Now this phi is a phase shift, and when we set phi to equal n pi, e to the negative j n pi is going to equal either plus or minus 1, which is why we have linear polarization. A special case of this is when either ex or ey equals 0, we will have either the line polarized along the x hat or y hat axes. A third special case occurs when phi equals 2k plus 1 times pi over 2, which gives us e to the negative j n pi over 2, where n is odd, and this equals plus or minus j. Now this plus or minus is only going to affect the direction of oscillation, not the orientation. So if we hold ex to equal ey to equal an amplitude, then we arrive at, in phasor form, the electric field equal to a x hat plus j a y hat e to the negative j bz, which will give us circular polarization, which is when we hold either z or t as constant and propagate along the other one, so t or z, and we arrive in the xy plane with a circle of radius a. So what happens if we don't hold ex to equal ey? Then we arrive at elliptical polarization, which is the most general form of this planar wave. So if phi is not in the form of phi equals n pi over 2, where ex equals ey and n is odd, or phi equals n pi, then we will have this ellipses in the xy plane. Now, you might notice that this general form is actually composed of an x hat and a y hat linearly polarized with a phase shift e to the negative j phi, which means that any elliptical wave is the sum of two orthogonal linearly polarized waves with a phase shift, in most circular polarization cases, of pi over 2. So the next topic I'd like to talk about is transmission and reflection. Now this occurs when an electromagnetic wave is propagating through one medium to the next, with both mediums having different permittivities and permissivities. When it strikes a boundary, which I will be calling the plane of incidence, the initial wave, which I'll be calling the incident wave, is going to partially pass through or transmit and partially reflect. Our goal is to determine the direction of the propagating wave that's being transmitted and reflected, as well as their field's amplitudes. This is a fairly complicated problem, so we are going to be starting with the simplest case, known as normal reflection, and this is when the incident wave is going to be propagating normal to the plane of incidence. If we define our plane of incidence as being along the xy plane, the direction of propagation will thus be in the z direction, which lets us have electric field and magnetic field along the x and y axes. So due to boundary conditions, we can see that the incident electric field is going to be in the same direction as the transmitted electric field and the reflected electric field. We can also see that the direction of propagation for the incident wave and the transmitted wave are the same, but this is going to be reversed for the reflected wave. As a consequence of this, we can see that the reflected magnetic field is also going to shift directions. This can be shown through equations for the different fields, being the incident, reflected, and the transmitted fields, and we can see that between the incident and the reflected ones, there will be a change in the direction of propagation, and specifically for the reflected magnetic field, we will see that the entire field shifts directions. We can also see that for the transmitted magnetic field, there will be a change in impedance due to the different permittivity and permissivity. Now, at the boundary, the following conditions must be met. We need the parallel to the boundary electric field to be equal on either sides, and the magnetic field parallel to the boundary must also be equal. This results in, for the parallel components, the transmitted electric field to equal the incident and reflected electric fields, and the same must occur for the magnetic fields. Now, as E and H are parallel to the interface, there are no normal components, meaning that this can just be said in general. So when we set Z equal to 0, we will be left with just these amplitude values for both sides of the equations, and we will arrive at E naught t equals E naught I minus E naught r for this condition, and for this condition we have E naught t over impedance 2 equals E naught I minus E naught r over impedance 1. So solving for E naught r, we get the following equation, which is known as the reflection coefficient. And using this, we can solve for E naught r, knowing only the impedance and E naught I. Similarly, when solving for E naught t, we arrive at this equation for the transmission coefficient, and we can solve for E naught t, knowing strictly the impedances and E naught I. So now we know the direction that the magnetic and the electric fields will go for all of these cases, along with the amplitudes of the electric and magnetic waves. One last thing to note before I move on is that 1 plus r is equal to t, which links these two equations together. Now, we have determined what will happen when a wave strikes a plane of incidence normal to the plane, but in a lot of scenarios, this wave will be hitting the plane of incidence at an angle, which we will call the angle of incidence, or theta I. Now, the direction that this wave propagates in is a vector, and we can separate this vector into a component normal to the plane of incidence and parallel to the plane of incidence. And for convenience, we will say that this plane is, again, along x and y, and the normal component will be z. We can represent this as the normed vector for direction, which is the wave number, and multiplying it by cos theta I for bz, and for bx by multiplying it by sine theta I. Now, as the direction of propagation has a z and x component, this means that the electric and magnetic fields are no longer along the x and y axis, and rather a linear combination of x, y, and z. The only constraint for these is that the direction of propagation is mutually orthogonal to the electric and magnetic fields. Another new thing with this model is that the direction of propagation for the reflected and the transmitted waves are also going to be angled, with the reflected one having an angle of theta r, and for transmitted, theta t. However, the parallel component will still be equal between these. So for the incident, reflected, and transmitted waves, bx is all going to be the same, which we'll just call bx. In addition, we have the incident, reflected, and transmitted frequencies all being the same, and we will call that w naught. So as the frequency of the incident component is going to equal the frequency of the reflected wave, this means that the incident wave number is also going to be equivalent to the reflected wave number. Now, as the parallel components of the direction can be given by this formula, we see that bx is equal to the wave number of the incident wave times sine theta I, and it's also equal to the wave number of the reflected wave times sine theta r, which means that the incident angle and the reflected angle are equal. Also, we see that the frequency of the incident wave is equal to the frequency of the transmitted wave, but for the wave number, there is dependency on the permittivity and the permissivity, and as the transmitted wave is in a new medium, we have a dependency of the permittivity and permissivity for bx, which leads us to the equation sine theta t over sine theta I is equal to the square root of epsilon 1 mu 1 over the square root of epsilon 2 mu 2. Now, we can let the square root of epsilon mu equal to the refractive index n, and we arrive at Snell's law, which states that n sine theta I equals nt sine theta t. So now we have definitions for all three of the angles, but we still need to figure out the amplitude of the two fields. And this can be quite tricky because the fields are no longer along a single axis, but have multiple components. However, we can break these fields down into only two components, and these are the transverse magnetic mode, which has the electric field parallel to the plane of incidence, where EY equals 0, and we have the transverse electric mode, where E is perpendicular to the plane of incidence, and HY equals 0. We also have a special case, which occurs when both E and H are normal to the propagation direction, and this is the transverse electromagnetic mode, which we have already seen in the normal reflection. So now I will analyze the transverse magnetic case, and we can see that the x-at and z component of the electric field have values, and that the y hat component is equal to 0. As the magnetic field is orthogonal to these, we have that the magnetic field is equal to the direction of propagation crossed with the electric field over an impedance, and that means that it is in the y hat direction. And we can see this visually with the HI and HT being in the y hat direction, and just like in the normal case, we have the reflected magnetic field being flipped. We also see that the electric field is going to maintain its shape, and it will always be orthogonal to the other two fields. Now, at z equals 0, we can again apply the boundary conditions. Parallel electric fields are equal to each other, and parallel magnetic fields are equal to each other. But in this case, we have an x and z component to the electric field, meaning that when we have the equation EXI plus EXR equals EXT, we are going to add cos theta I, cos theta R, and cos theta t to this. The magnetic field equation is going to be the same as for the normal incidence reflection. And from this, we have the two parameters for this. We have the reflective coefficient, now with a dependency on the angles, but still using the same format of impedance 2 minus impedance 1 over impedance 2 plus impedance 1. And we have the same thing for the transmission coefficient with the same dependencies now on theta. Now, the difference for the transverse electric case is that instead of having no EY value, we only have Y hat value, and the electric field components for X hat and Z hat are set to 0. Now, as H is orthogonal, we have H being in the X hat and Z hat directions, which is opposite to the TM case. And we can see here we have the H and the E fields switched places, and we also have the E components now swapping for the reflected case. Our coefficients for reflection and transmission are largely the same, but the key difference here is that the EY value is not going to be dependent on cos theta, but the magnetic field is now going to be dependent on cos theta. And if we look closely at this in comparison to the transverse electric case, we can see that the values of thetas have switched from theta t to theta I. So now that we've wrapped up our analysis of the TM and TE modes, we can go back to our initial problem, which is determining the amplitudes and the angles of the incident, reflective, and transmitted waves. And we have done that now. In instances where there are X, Y, and Z components, like in this diagram, for the incident and reflected waves, we are able to use the principle of superposition to combine the TE and TM solutions for this issue. Now, we have also gone over the approach for normal reflection, which is the simplified version of this issue. And at the beginning of the lecture, we went over polarization in its linear, circular, and elliptical forms. Thank you for listening to my discussion.